All right, good afternoon. Hello. Good afternoon. How's everybody today? Good. You know what? I'm gonna grab a microphone instead of sitting. You know, I'm standing here behind all these guys. I don't know. Okay, does this work? Now? Yes. Okay, great. That's better. Thank you. Well, thank you all for being here this afternoon. It's just phenomenal to be celebrating the first Arizona Tech Week. Thank you to the Arizona Commerce Authority, of course, for pulling this together. What an amazing series of events all across the state. I mean, what a great idea. I've never heard about another state that does something like this for a whole week. Maybe there are. I just have never encountered anything like that. So I think it's phenomenal that we're actually celebrating innovation, that we're celebrating technology, that we're celebrating everything that the state of Arizona can bring to the table to help advance our economies. And at this panel here, we're going to talk about something really, really exciting, which maybe is out in the future, but honestly, that's also what we as a university and our partners are about. It's about thinking about the future, right? If we don't do it, who's gonna do it? So you're gonna hear about fusion today. And we're gonna talk with the panel about why fusion and what are we doing. There's a very fundamental reason why we're doing this, and it's one of our key strategic initiatives here at the university. And it's because we believe that ultimately, as a society that populates planet Earth, we need clean, sustainable, abundant energy for the entire planet. And there are many ways in which that can come about, many sources of energy that will contribute to that future. But there is one particular source of energy, the energy that powers the stars, right? Fusion, that really, if we're able to conquer it here on Earth, can make a huge difference to the future of the planet. Can bring energy abundance, not just to Southern Arizona and the state and the nation, but around the globe, in ways that are infinitely sustainable, sort of baseload, clean, safe, secure, something that truly could move the planet forward in a direction that we haven't been able to experience before. We live in a world of energy scarcity, right? All the time. We worry about energy. Where's it going to come from? How are we going to power the data centers? Look what is happening with the Strait of Hormuz right now. What a mess, right? A little bit of conflict, a lot of conflict, and energy prices go through the roof, and we don't have enough. We need to change that mentality. And so that's what you're going to hear about today. It's about how do we change the mind frame, the mindset, from one of energy scarcity in which we cannot desalinate water. We worry about water in Arizona, right? We worry about the Colorado River. It didn't snow this year, barely. I was with the Secretary of the Interior earlier this week over at the San Javier mine, and we're talking about mining and critical minerals. But guess what? Most of the conversation and all the questions from the community that were directed to the Secretary and his staff were about water. What about the Colorado River? So imagine if we could just easily, cheaply desalinate water, right, all the time. It would change the way we think about abundance. It would change the way we think about how we use the land, how we produce food. It would change food security. It would change energy security, everything. So anyway, that's what we're about here today. I'd like to introduce to you Dr. Horst Hahn, who leads our Fusion Energy Initiative here at the university. Horst.
Good afternoon, and thanks to the audience to come in a good number on a nice day to make it to this very beautiful building. And thanks, Thomas, for introducing the topic and how the university came about this strategic research area on fusion. I would like to, before I introduce the panelists here to you, I would like to start with a few opening remarks to get us all to a starting point that you can follow this kind of discussion we will have here, also without knowing too much about the physics and the background of fusion, but you should have a few terms which you should know. I mean, you may already have heard something about fusion, the fusion we talk about today, but fusion is also, in other terms, in other parts of our society, there's also a fusion cuisine, right? So what do you do there? You blend different ingredients together to create something new, right? And so we all enjoy that sometimes if you go to a fusion-type restaurant. In physics, fusion also means to bring things together, but now at the level of atoms, or better, at the level of the nuclei of the atoms. And this is what is the process that powers our sun, but also the other stars. In the sun, it's hydrogen atoms, or better, their nuclei, which are forced together to form helium. So you really transform a nuclei of hydrogen, or two nuclei of hydrogen, into helium core or nucleus. And this releases enormous amount of energy. And this is what you would like to harvest also on Earth. We do that already every day on a sunny day like that, but even on a cloudy day, we survive here and our plants grow and everything flourishes because of the sunlight that comes to us. And this is what is transported from what originates from the nuclear fusion that happens on the sun. So the same process we would like to take and do it on Earth. But in the sun, we have a very large mass which brings together by gravitational forces, brings together the atoms into what is called a plasma, where nuclei and electrons are separated, and you have a high energy plasma at very high temperatures inside the core of the sun, and that is a condition for the atoms to fuse together, or for the nuclei, I should say, to fuse together to form the helium. We cannot do gravity on Earth on that magnitude that can be done in a star. So we have to find other solutions. So we use advanced technologies, for example, very powerful magnetic fields that can confine the hot fuel, which is called the plasma, or we use intense laser pulses that can rapidly compress the fuel to get temperatures which are even much hotter than in the core of the sun. And under those conditions, we can also get fusion on Earth. And this has been demonstrated for the first time ever on Earth in an experiment at the National Ignition Facility at Lawrence Livermore National Lab on December 6, 2022. So the physics is proven. Now we have to transfer this into a technology. So, and this is what is kind of the area that we have identified here at the University of Arizona, that we would like to work mostly on solving these engineering problems which are there. And I have mentioned already things, like 100 million degrees of temperature. This is something which we cannot even imagine. But you have these temperatures in a fusion reaction, and we need to deal with that, and there are ways to do that. So this is what we would like to talk about today. So let me very briefly introduce our panelists, and I would ask each of you, when you have asked for the first time a question, to say maybe a few more words. I just mentioned your name. Next to me is Patrick Kiefer from Leonardo Electronics, a local company here. Then we have David Hahn, he's Dean of the College of Engineering. Then we have Sammy Tin, who is the chair of the Material Science and Engineering Department. And we have Mark Spencer, who is from the College of Optical Sciences. And of course, you know Tomas Diaz de Rubia. He has given the introduction here. So with that, I would like to turn to the first question. And I would like to ask Tomas, because he has to leave soon, a first question. And why do we focus on fusion instead of energy technology we have already today? I mean, we have power, we could build more gas power plants, and why do we concentrate on fusion?
Well, I mean, look, I think that's a very good question that should be asked. I think the way I think about it is not instead of, but it's in addition to, right? We need energy solutions today. fusion is not the energy solution today. It will be if we have our way in 10 years or something like that. But we need energy solutions today. At the state of Arizona, we need more energy to continue the economic development that is happening in this state over the last decade. We have a tremendous demand for data centers. We have population growth in the state. We have TSMC and other major corporations coming to the state. We have a lot of companies around the globe who want to have a presence in the state of Arizona. We need more natural gas. We need more solar panels, more solar, utility scale solar and storage. We need all of it. We need geothermal energy. The governor's energy task force, in which President Garimella was a member and that I participated in, just put out a report last week that calls for, sort of puts out ideas and sort of what the state government plans to do regarding energy demand and energy supply in the state, but also talks extensively about geothermal energy and about nuclear. We need all of that. But ultimately, at the end of the day, in the future, we want to reach this critical transition from fossil fuels and other sources of energy that perhaps can create social construct complexities like nuclear waste, to energy solutions that are, again, clean, no greenhouse gas emissions, sustainable. Hydrogen is the fuel. Hydrogen is in water. Dispatchable, meaning that it's base load. It doesn't matter whether the sun is shining or not, or the wind is blowing or not. That create no long-term radioactive waste of any sort. That have no safety concerns regarding, reactor explosions or things of that nature, and they're inherently secure in terms of, proliferation of nuclear materials and things of that nature. That's fusion. That's why we're doing that. So it's not instead of, but it's rather in addition to. We here at the university, the Geological Survey is here at the Arizona Geological Survey is here at the university. We're working with the state governor, with the governor's office on geothermal energy. We're working on other forms of energy, of course, on battery storage, on many, many other things. But we thought that focusing on something like this, which is really outwards, forward-looking, would be really important for us to do. There is right now, to give you an idea, there is right now about $12 billion of venture capital going from the private sector into new startup fusion companies. Thank you so much. New startup fusion companies all around the country, and this is happening in Europe also, that are exploring different ways to get to what Horst talked about, which is how do you get to those conditions of hundreds of millions of degrees and billions of pressures, billions of atmospheres of pressure. Think about this. We're sitting here at 1 atmosphere of pressure, right? That's the sort of the baseline. Inside a fusion reaction, you're about 10 billion times the pressure that we feel here at 100 million degrees. How do you get to those conditions? $12 billion of venture capital, federal investment around the world going into this concept that we need to get there. There are many different approaches, but we think that by focusing ourselves and working with private sector companies and the federal government, we can help accelerate that transition from the science that Horst talked about that happened at that laboratory in California, from that science demonstration, which was tremendous, but it was a science experiment. Nobody think that was anything close to actual commercial fusion. How do we accelerate that path to commercialization? That's what we're trying to do. That's what the panel is going to talk about. How do we get there fast? How do we get there faster than adversaries around the world that may want to get there before we do? Because guess what? This is going to be a multi-trillion-dollar business in 15, 20 years. Okay? This is not the countries that control and that get to market first with fusion energy will control energy markets around the world. So this is a national security issue. It's not just, hey, it would be nice to get the conditions of the sand down here. Let's go figure out if we can do this. This is truly a national security issue. And that's why we're focused on it.
Okay, thanks, Thomas. My next question goes to David Hahn, and it is like, what makes Southern Arizona uniquely positioned to play a leading role in fusion research and commercialization?
Thank you, Horst. It's great to be here with all of you. I know many of you, with my colleagues from engineering, from optical sciences, from industry. We should have a good discussion. Thanks for framing things so nicely, Tomas. You know, Southern Arizona, it has an innovation ecosystem, and I think I'm deliberate about both words. It's an ecosystem that is built around innovation. As companies large and established, the Raytheons, the Leonardos, the modular mining that's heavily invested in autonomy. So all of that is there. But then we have Optics Valley, a broad range of companies that are working on optics, lasers, electro-optical devices, all those necessary ingredients. And then we have a long history of taking on energy and renewable energy and sustainable energy. So when you look at the key ingredients, they're there. And then importantly, we're sitting on our campus at the University of Arizona. We are a catalyst and we are a key partner. We often talk about the importance of bringing academia with our education and workforce, our innovation mindset with our industry partners, and then with government. It's those three-way partnership that will allow us to take on a problem like fusion. None of us can do it alone. None of those sectors can get where we need to go. We have to have the university, we have to have industry, we have to have government. We have those ingredients here, and our role is to help bring that together. And then finally, we have workforce. You know, the University of Arizona is a workforce pipeline that is feeding this ecosystem every day, every semester, and that's a key ingredient. So when you really bring it all together, Horst, it's the opportunity, it's the land, it's the infrastructure, it's the people, it's the talent, and it's the mindset. And I think collectively we can take on these problems that have this 10-year time horizon or more and consistently work at it and make progress and move this forward. And it's an exciting time that all these pieces are right here in Southern Arizona.
Thank you for, with a lot of excitement, to point this out.
Absolutely.
So I think this is what we need, to have this excitement for the field, for the university, and also to transfer that to our students and postdocs and colleagues. Next, I would like to ask Mark Spencer from Optical Sciences. Until very recently, he was more on the funding side. Now he's on the receiving end here, and I would like to ask him, fusion, as we also heard from Thomas, is seeing growing investment from the private sector. And with the agencies like DOE or DOE, it's a bit slower. And but where do you see the biggest funding opportunities right now for us to really address and tackle these problems? And how are these shaping the direction of research towards commercialization?
Yeah, thanks, Horst. Really appreciate the opportunity to be on this panel. Thanks, Tomas, for your leadership and putting together something so meaningful. So Mark Spencer, I'm a professor in the Wyant College of Optical Sciences. Before this, I've been a professor for about a semester and a half now. Before this, I was at the Pentagon, believe it or not. I was the director for the Joint Directed Energy Transition Office. I executed about a $200 million budget. And then I got the opportunity, the honor, the privilege to take my boss's job before I left, which was to serve as the acting principal director for directed energy. That's the senior most official in the department for directed energy. So high power microwaves, laser systems for defense purposes. And the budget there, for example, which speaks to your point, Horst, the budget in the Department of Defense, the Department of War, before I left in directed energy, it was on average about $1 billion per year across the services. Army, Department of the Army, Department of the Air Force, Department of the Navy. Actually, we had a lull where it was about $700 million before I left. But the new administration came in and there is a need. And that budget grew from $700 million to about $2 billion before I left. That was in August. And since I've left, I think it's grown to about $3 billion. So the budgets are going up. That's on the DoD side. On the DOE, I'm sure given some of the points that Tomas made and the tie to this is a national security endeavor as well. I'm sure the budgets are going up for things like fusion as well. So we have to have the leadership, the strategy, the vision at the university to play a role. And I think there are several opportunities out there. Horst, to your point, I like the strategy and the vision that you've laid out here at the university, which is, hey, let's go team with some of these companies. Maybe they're big, like a Leonardo. Maybe they're more small, working off of venture capital. But let's team with these businesses that have IP in this technology. It's going to leverage critical technology like optics and photonics. Dean Hahn just mentioned this point, and the Southern Arizona community can get after it. The Wyant College of Optical Sciences, we're the largest, the leading institution for developing optics and photonics technology, and we get a team with great colleges like the College of Engineering, for example, to get after it. So I think teaming with these businesses in the future that have developed IP, teaming with them in a robust way to further develop, say, patents, proving out the patents, but also developing the next generation along the way. I see one of my students in the audience as we speak. This isn't going to happen overnight, and if we don't chip away at it in a strategic way where we get the next generation involved early, we're not going to make it. So the money is out there. The money for things like fusion, the funding from the Department of Defense, Department of Energy is out there, but we have to have a strategy and a vision, and I think we have that here at the University of Arizona, and I'm so excited to be part of it. Thank you.
Thank you, Mark, for your explanations about the funding situation and your view, and also for pointing out the importance of our workforce and the students who have to be trained or should be trained to move to these companies in the future. So next I would like to really address the industry partner here, Patrick. Where do you see the most promising collaboration opportunities today, and where does the supply chain, which you are covering, become a critical piece of making fusion a reality?
Thank you, Horst. First, just to echo the points of everybody else, it's a pleasure to be here. I mean, I'm on a panel with some brilliant people that have been working in the field for quite some time, so it's both encouraging and also quite intimidating, but I'll try to make it through that part. And also to follow up on some of the previous questions, you know, to the point of national security, the collaboration, not just at the university and the DoD level and DOE level, but with industry is extremely important. You know, we can have all the best scientists and we can even have power plants that are producing power, but if we're not supporting the supply chain, then there's no reason for these power plants to purchase locally, and that supply chain could be shut off. We don't have control of it, things like that. So it's very important for us to continue the collaboration with diode manufacturers like myself at Leonardo. So that's been really encouraging to see so far. To get into specifics, I think, Horst, the easy answer is the most promising collaborations, the ones that we're involved with directly. So that would be Starfire, which is a DoD-led hub, a research hub. It's funded to the tune of $16 million, focusing on the commercialization of some fusion technologies. So again, that's really trying to make sure that we have this tech transfer going from kind of the ideation that's happening at the university level into the manufacturing. In addition to this, we have the Bridge program, which Horst and I are working on directly, and that's focusing on making sure that the national labs and the industry are, collaborating on test stations and working together to support each other on test facilities. So, as an example, one of the key questions we have is diode lifetime. So. Hopefully I'll get a chance to get into some of diode technology in a little bit, but there's massive amounts of laser diodes that are required for these fusion plants in the future. And just to give you a scale of things, if you sum the entire production of high-powered diode lasers across the globe, there's not enough being fabricated to provide enough diodes for a single power plant right now. In fact, it would take you 30 years to get to that quantity. So there's a lot of acceleration that we need in terms of our manufacturing capacity, and the types of efforts that we're working on right now on the Bridge and Starfire program are hopefully going to address that.
Okay, thank you for pointing out another big challenge, in the supply chain. Thanks a lot. Next question, I would like to start with Sami Tin, and want to ask him about what are, in his opinion, some of the biggest technological challenges that still need to be solved to make fusion commercially viable, and where is progress happening the fastest?
Thanks, Horst. Again, it's a pleasure to be here in front of this audience talking about fusion. But that's kind of a loaded question when you ask, what some of the biggest technical challenges are. When you ask that to material scientists, we're going to say it's materials, right? So, we're in the business of creating design-enabling materials, right? So I'll give you an example. 25 years ago, smartphones did not exist. Steve Jobs had this crazy idea about, combining an iPod, a Palm Pilot, and a flip phone all together into a compact unit. His engineers thought he was crazy, but, a few years later, the smartphone has become quintessential for everybody, right? Fusion energy, it may sound like science fiction, but it's only science fiction until the right materials and processes come along to make it a reality. That's what I tell, all the students that listen to me, at least. When it comes to fusion, obviously, one of the biggest technical challenges is getting really, really high energy lasers, laser diodes, right? Making them high energy, making them efficient, making them reliable. Again, it's finding the right materials and manufacturing processes in order to kind of produce the laser that will provide enough energy to get that initial ignition event. The second, technical challenge is a manufacturing challenge related to, the production of fuel pellets. You need tritium and deuterium ice contained within a diamond capsule, right? How do we mass produce hundreds of millions of these capsules in a very efficient manner, right? It's a materials and manufacturing challenge. Third is, once you get ignition, how do you contain that fusion, right? It's a very extreme environment in these fusion reactors. You have high energy X-rays, you have neutrons, you have helium, right? How do you create a material that can basically withstand the energy of the sun, right? Materials for first walls. And then the other big materials challenge in my mind is, you need to be able to breed tritium, right? How do you breed tritium? You use these these liquid lithium breeders. How do you contain that? How do you make that reliable enough so that it lasts 15, 20, 30 years, right? So all these technical challenges need to be overcome before we can realize fusion, right? And as Tomas was mentioning, energy has become a commodity, not just for national security, but for a way of life, right? If we want to, go forward, our next generation of people are going to be completely reliant on AI. How do we continue to develop AI? Energy, right? So it's become essential for continuing technology and development into the future.
Mark, staying on the same question from your view from optical sciences and for your background, what do you see as biggest challenges?
Sure. So thanks, Horst. I am the laser guy, or I am a laser guy. I use lasers, and let's just assume that we have the energy needed. I'm staring at a picture. I think it's up on the screen there. I couldn't ask for a better example. Imagine each one of those little blue lines is a laser beam. You got to get those beams inside what we often refer to as a target, where the hydrogen is, and you need to confine it with the energy. So getting all those beamlets pointed in the right direction is not non-trivial. That's actually my area of expertise, is beam control, tracking. How do you track the target? How do you operationalize this capability where, yes, we're going to mass produce these targets with the hydrogen inside them, and then shot after shot, we're going to reliably direct these laser beams, direct the energy into the target, and get the fusion out of it. I had an internship back in 2008 at Lawrence Livermore National Laboratory at the time. Yeah. At the time, NIF was coming up online. NIF is the National Ignition Facility. So I got to see it in kind of its infancy, where the lasers were just coming online. And then in my past role, I got to visit and see, hey, this is no kidding working. And that just, to the what it's designed to work at. So that's a big investment from the Department of Energy. It's a sustained investment. It has reduced a lot of the risk associated with this technology. The job's not done. That is more of a science and engineering sort of capability. It's to reduce the risk. We need to operationalize this technology, shot after shot, reliably produce the fusion. So that's where my thoughts are. Luckily for us, it's becoming more of an engineering problem, less of a foundational science problem.
Can I also add? Well, can I add, Horst?
Please, go ahead.
So I'll kind of take what Sammy did as a material scientist. So if Suresh Garamella were with me, him and I would both say it's mechanical engineers, thermal management, right? And he would be right with me on that. We have to manage this heat, right? It's a pulsile generation of high loads of energy. So what are the working fluids? How do we manage that load to transfer that energy out of this core millions of degree rate control volume into a working fluid, out into a secondary working fluid, and translate that into energy? Those are really challenging problems, great problems for a thermal engineer to take on. And, in a half an hour, a commercial plant would have more shots than NIF has had in its lifetime. So huge thermal loads, huge impacts. We're not going into basically a quiescent medium anymore. We're going into something 10 times a second with huge doses of energy. So great thermal management problems, and we have that expertise on this campus. So that's an exciting aspect.
Great, thanks for adding this.
Let me, because I don't know how many of you are familiar with, you're hearing about NIF, the National Ignition Facility, where he did his internship. So imagine 3 football stadiums put next to each other, right? That's the size of the NIF laser. So typically when you think of a laser, you think of a laser pointer, right? Something like that. So now think about 3 Arizona football stadiums next to each other. That's how large the NIF laser is. It was at the time, when he was there in 2008, 2009 is when the NIF was actually commissioned to start operating. The cost to the government in 2009 dollars was about $3 billion, which is about 7 today. It was a massive investment by the US government to demonstrate that you can actually, scientifically conquer fusion on Earth. These laser beams, again, you think of a laser pointer, these laser beams are 40 by 40 centimeters. There's 192 of those that eventually get focused, as you see in that picture, into a tiny millimeter-sized pellet that contains hydrogen fuel, isotopes of hydrogen. That pellet, the beams. Sorry, I just want to make sure so you follow some of the conversation. Why are these things important that they're talking about? Those laser beams that you see they're going into a cylinder. That cylinder is made of gold. Those laser beams impact the cylinder and essentially vaporize the gold and create X-rays, very high intensity radiation X-rays, like when you go to the doctor, right? So massive amounts of X-rays that then illuminate the capsule in the center. The millimeter capsule explodes because of the X-rays, and the fuel inside implodes at 1,000,000 miles an hour. 1,000,000 miles an hour. Okay, it goes from a millimeter to 30 microns, 30 millionths of a meter, very, very fast at 1,000,000 miles an hour. If you do that right, right? And avoid what we call instability. You know, imagine you have a balloon full of water and you try to squeeze it down from its size to 100th of its size very quickly. What happens to that water, to that balloon? Say water is squirting everywhere, right? So imagine if you do that right, then you get fusion. So it's hard, right? It's not easy. And as Dean Hans said, now you got to do that, 10 times per second. So the challenges are not for the faint of heart, okay? And that's why the University of Arizona, that's why we're working on this.
Thank you, Thomas, for highlighting that. And I always admire how excited you are about this, having grown up there at NIF, and, that's really wonderful. I mean, there are two very hot fields, and among others, one is AI, of course, and we learned about the Genesis call by the Department of Energy. The other one is, of course, what we are trying to do here, fusion. So what are here the tools that we can develop together, AI in fusion and so on? We said, we need electricity to do AI, but now what can AI do in order to get fusion in fusion research and system design? So David, you want to?
Yeah, thank you, Horst. I appreciate you using the word tools, right? Because AI is not going to do our job. It's going to allow us to do our job more efficiently for this. And that's what we're trying to teach in our college every day to our young engineers. So we have a lot of ways to use AI to advance this. I mentioned specifically thermal management a little while ago. So we can suddenly take AI tools to model the entire heat transfer problem through that reactor and parameterize that. So we got a spatial, temporal heat transfer problem. Let's put that into an AI model rather than a simple analytical model, have some sophistication, parameterize the design space, and then optimize that system. That's something that without AI would be very complicated and lengthy to do using the traditional tools. So that opens up a whole new space to help tackle this thermal design issue. And then when we talk about the first wall materials, back to Sammy here, how do you deal with these hard radiation impacts, these high thermal loads? And now there's some amazing AI tools that do predictive property analysis. So we have machine learning tools. I pulled these off the internet. Roost, CrabNet, you know those, Sammy? They're out there, and they allow us to predict material responses to things like stress and strain, thermal expansion, band gap analysis. So suddenly we can start to tackle this without having to go in and experimentally validate everyone. We can narrow down, pick a few, and go from there. And then this opens up a whole new space, which is really inverse design to design new materials that we don't even have every day. And there's a program called MatterGen that's developed by Microsoft. So now we're using generative AI to create new stable inorganic materials that we can put in design spaces, radiation hardening, thermal management, conduction, conductivity, and suddenly now we can start to say, hey, here's a new concept that might not even have on our shelf right now. So when we put all these tools together, it allows us to really start to advance this in ways that would have taken a lot of time before. And I'll end with where I started. We still need the engineers and the scientists to use these tools, but they allow us to do things faster. As Tomas said, we need to get this going. This isn't another 50-year horizon. Let's tackle this problem in a decade. These tools can help us go faster using our overarching engineering and science skills, and then taking this faster.
Well, thanks a lot. I would like to also ask Patrick here about the industry side of that question. Is that something that is done in your part of the industry, or do you know of any other activities?
Absolutely. Yeah. So I think on the industry side, the holy grail is what's called a digital twin. And that's taking your AI models and really completely digitizing your plant. That allows you to simulate design choices you may be considering that if you were to do it in real life might cost millions and millions of dollars. Well, now you can do it inside your computer, and you can game plan things like what is the appropriate size of the reactor. What happens if I make my reactor too small and now I have damage on the inside wall that I have to manage. There's a million questions that can be answered in simulation space now. I was at a conference a couple weeks ago, an inertial fusion conference, and it seemed like every other presentation was mentioning AI. Livermore's got their own AI. You mentioned Genesis out of the DOE, which is linking all the national labs and collaborate, pulling all of the different pockets of many years of research and data and making it accessible to the engineers. And I think someone mentioned earlier, it might have been you, Mark, that I think we're at a stage where the fundamental physics hopefully has been solved and it's been demonstrated by Livermore. And really we're looking at engineering problems, and that is a perfect area for AI to be utilized, because AI, maybe in the future could be used for fundamental physics discoveries, but really it's collecting information that's been generated by the scientists and making it available and solving problems quickly. And that's the exact type of engineering problems that we have in front of us. So I'm extremely hopeful and excited to continue to work with AI and see how those models grow and see how quickly. 10 years might actually be a realistic number. It's kind of crazy to think about, but yeah.
Great. Thanks a lot for your insight for that. I would like to stay with you, Patrick, with the next question. It's related to workforce and what kind of talents and skill sets are needed in industry to support the growth of fusion energy, and how can university like U of A, whom you know very well here, right, help prepare that workforce?
Yeah, I love this question because it's extremely important. I think, so there's a couple points I want to get across. One of them is that I think young people might be intimidated by the topic or some of the job titles of positions that are out there in industry, but they really shouldn't be. I was talking to a colleague at the same conference, and she got a bachelor's degree in economics, ended up getting a master's degree in mechanical engineering, and then is now working on AI-driven economic plant models at Livermore. So, really what we need as a community is not, specialists are great, we do need specialists, but we need very well-rounded people, we need curious minds, we need people who can go out and solve problems, who are interdisciplinary. And so it's critical. Some of the design choices that the laser guy makes are going to affect the reactor people and the target people, and vice versa. And if we're not able to understand the pain points of each other's problem sets, we're not going to be able to converge on a solution that works for everybody. And so I think the university hosting panels like this and educating on multiple topics simultaneously in the inertial landscape is critically important. I think continuing to support internships in industry and at the national labs that the university is currently doing is excellent, and also reaching out beyond the university level and looking to educate the educators at the high school and middle school level, because as we've learned from STEM outreach over the past 20 years, if we start in college, it's too late. We really need to be starting. We need to be teaching fusion in kindergarten, maybe.
Well, maybe we do the next panel there.
Yeah.
Anyway, thanks for your insight. I would like to add that in the Starfire Hub project that the University of Arizona is also involved, which is led by Lawrence Livermore National Lab, we also have an online course which was taught the second time this spring. And it's online. Each time we had more than 100 participants listening to the talks and courses, lectures of the experts in various fields. It's an introductory course, and if you hear about it, I can only strongly advise you to listen to these talks, and it's very nice for that. Thank you. The next talk goes a little bit into realistic timelines, which is a bit complicated, but it's a wild guess almost, right? Because of so many challenges, but let's try it anyway. So David, maybe you want to start? What is a realistic timeline to get something?
Thank you, Horst. I do want to do that, but I want to just say a few words to kind of frame energy growth and demand, right? And so, because that's really the problem we're trying to solve. So, projections from Bank of America, IEA, they're looking at compound annual growth for power needs in the United States of 2 to 3% annually from 2030 to 2035. That compares to 0.5% compound annual growth over the last decade. So 4 to 6 times the energy need in that coming decade. And that translates to capacity of about 128 new gigawatts of generation. And depending how you count your power plant capacity, that's roughly 60 to 100 new nuclear power plants of the current scale. So that's big energy needs. And so, when we look forward, some of the bottlenecks now are the time to get power online, and goes back to the time frame that's necessary to affect impact. It average takes now about 5 years from sort of initial conception of new generation to going on grid. And we have about 2,000 gigawatts of backlog of planned power. So, as a nation, we have plans to put power online, but we have growing demand that will need every electron that comes out of those plants. So really, when you look 20 years out, projections of 50 to 200% needs beyond current capacity, that's a huge power. And so when you talk about time frames, I think kind of looking at a 20-year number to be there when that demand is coming on is a good timeline to shoot for and aim for. The practicality of that, we've talked about it. Patrick said, we need thousands of times more, 30 years of production of diodes over to current capacity. We've got to solve those technological problems. But I think you're talking about that kind of 20-plus year time frame to try to get these things on grid. I'd love other people's opinion of that. Tomas, you want to comment on that?
5 years, come on. Let's go faster. It's a race. It's a big race. China is investing probably 10 times what the U.S. is investing in trying to get to fusion on the market. So it's a real race. I think Dean Han's timeline is very appropriate. There's a lot of supply chain and challenges that need to be overcome. Even today, to the point he was making, if you want to fire up a new gas-fired power plant in Arizona, it's a 5-year delay because of supply chain, right? The generators for new gas-fired power plants, we know how to build gas-fired power plants, right? It's not complicated, but it's about a 10-year delay from the start of, decision to invest by a utility to putting electrons on the grid. So we're in a tough place right now when it comes to. The other day I heard the CEO of APS, Arizona Public Service, talk about since the financial crisis of 2008 up until next year, energy demand growth in Arizona was essentially flat, right? Maybe 1% or something like that. Over the last couple of years, it's been 17% per year, right? Because of the tremendous economic growth that the state is seeing. And so at the end of the day, I think the answer to the time frame is going to be very dependent on investment, how the federal government supplements the investment from the private sector to get to market fast. I don't believe that the private sector with venture capital, even at the $12 billion investment level, can get there. It requires a public-private partnership. Unfortunately, I'm not seeing the sort of increases in funding for fusion energy at the federal level that I was hoping to see over the last year or two. This administration has made fusion a priority, but the dollars haven't really changed very much. So I think it's going to be very dependent on that. I'm hoping that we're going to accelerate, that the federal government is going to start putting more energy and more focus and more funds into partnerships with the private sector. But right now, I don't think it's sufficient. So I'm worried about it. I think we can go fast, but it's going to be very dependent on resources.
Yeah, so I'm glad you brought that up. So right now, the diode lasers. So there's I mentioned earlier there's these AI models, these economic models that try to figure out what is the cost of a component needs to be in order for these plants to be economical. And at the diode level, that goal is 0.7 of a cent per watt. Which, if you don't have a point of reference, it's like fine, whatever. But we're closer to 80 cents to $1 per watt right now. At 0.7 cents per watt, the diode lasers make up 46% of the plant costs. At 10 cents, test. Okay, at 10 cents per watt, it's 90% of the plant cost. And so there's, and that burn down of cost doesn't happen automatically. So right now what we're seeing in industry, there's a bit of a stalemate between the startup companies who need the components to be at the price they need them to be in order to be economical. But industry needs that funding, that money injection to have the pipeline established. So I'm hoping that the DOE realizes that, and I think they're starting to understand. But to your point, that the money's not flowing yet, hopefully soon. But we really need the government to come in and break that stalemate. I think that's critical to achieving any timeline, let alone 10 to 20 years. Yeah.
I think to be very clear, right, we talk about how the science is difficult and, there was a scientific breakthrough and that's all great. The engineering and the technology are very difficult. The risk is still very high. And so that's where the federal government comes in. Right? It's great to see all the venture capital going in, and hopefully there's going to be more of that. And venture can take a lot of risk, but only limited risk, right? Because investors, venture capital is not a charity, right? The investors want a return. And these are very patient investors. You don't invest in Fusion if you don't have a lot of patience, because it's not an app, that's going to come out and, you're going to be in and out of your investment in a few years. This is a decade-long sort of capital, very patient capital, but you still need the government to help reduce the risk.
Well, I would like to thank the panel and, also that Thomas State. And I would like to thank, of course, all of you for participating, for listening, and also being active in the discussion. And as we were told, we can continue over there in the Café Bolo, I think, and talk, bilateral, trilateral, whatever groups we can form. Thanks a lot for coming.